Welcome to lesson 3 of our chapter 3, part 3 material. We're going to be reviewing logarithmic functions today and using ln. So if you recall from way back in chapter 1, when we started talking about e, we talked about a special logarithm that was log base e, and we write that as ln x or ln x, and this is called the natural logarithm. So just a reminder that logarithm is the inverse of an exponential function. So you had a lovely little conversion that you would have used last year, which is if you have, oops, getting my equals, writing too fast already. Log base a of b equals c. The exponential form would be a to the power of c equals b. So you can easily convert between logarithmic and exponential form. If we were talking about ln, if you have ln of some number a, then the matching exponential would be, sorry, again, going a little fast for my own good here. You have ln of some number a equals c. This would be the same as e to the power of c equals a. So ln is really just a log with base e. Okay. So if I want to evaluate some logarithms, what we're really looking for, if we're asked to evaluate a logarithm, is the base to what power gives me the inside stuff. So this first one, we have a log base 4 of 1 over 16, and we want to know, what does this equal? That's what we're trying to find. So if I rewrite this in exponential form, what I really want to find is 4 to what power gives me 1 over 16. This is what I'm looking for. 4 to the power of negative 2 would give me 1 over 16. So therefore, log base 4 of 1 over 16 equals negative 2. The next one, log base 27 of 3. We want to know 27 to what power gives me 3. Well, I know the cubed root of 27 gives me 3, and cubed root is just 27 to the power of 1/3. So that means that this is equal to 1/3. Log base a of 1, I want to know a to what power gives me 1. Well, any base a to the power of 0 would give me 1. Now, as soon as I have ln, what some of you will do when you start with ln is you'll change this to log base e each time. So if you really want to, if you don't like looking at it this way, you could rewrite this as log base e of 1. Okay? Which means I'm looking for e to what power gives me 1. Well, we just said log of any base a, the inside stuff is 1, this equals 0. So this would equal 0. Okay? Because of that right there. Okay? Which means that ln of 1 equals 0. And that's because e to the 0 equals 1. Okay? Now, what if I have log base a of a? A to what power gives me a? A to the power of 1 would give me a, so this is equal to 1. Ln of e is also equal to 1. And again, if I want to rewrite this, I can rewrite this as log base e of e. And so that would equal 1 because e to the 1 equals e. If I have log base a of a to the power of x, we need to apply our exponential power log laws here, where we can bring the x down in front. Log base a of a is equal to 1, so this just equals x. Similarly, we can use the same log laws if we have ln of e to the x. We can bring the x down in front and have x times ln e. Ln e is 1, so this gives us x. Okay. If we have a to the power of log base a of x, first, we don't know what this equals. So I'm going to say this equals some number y. Now, if I log both sides here, I'm going to log base a, since the base of our exponential is a. I'm going to log both sides. If I log both sides, on the left, I can bring that exponent down in front, and I'd have log base a of x times log base a of a. Now log base a is 1. So I get log base a of x equals log base a of y, or x is equal to y. In other words, a to the power of log base a of x is equal to x. So this was equal to 1. So I logged both sides, brought that log base a of x exponent down in front, and I said that this whole thing was equal to some number y, and at the end I got that y was equal to x, and that would be the same x that was in the very original equation or expression there. So if I have any base to the power of log with the same base of some x value, it just equals that x value. Okay? Which means that next one, I could use the same logic. This should also equal x, and that's because this is e to the log base e of x. That's all this is. And we just showed that if the base of the exponent and the base of the log are the same, then you will get x as your answer. So I could go through the exact same process. I could say e to the ln x equals some number y. I would ln both sides, because log both sides, you want to use the same base as you have in your exponent. So if I ln both sides, I can bring the exponent down. Ln e is 1. So I end up with ln x equals ln y, or x equals y, which means e to the ln x is equal to x. So all of our log laws that we're used to using from grade 12 apply to ln as well. All ln is, our natural logarithm, is a log with base e. Okay. So just a refresher about what these graphs look like. If you have an a value bigger than 1, your graph looks like this. You have an asymptote on the x-axis, and your intercept here is 1, 0. If you have an a value between 0 and 1, you also have an asymptote on the x-axis, and your intercept is still 1, 0. And the same correspondence between your log and your exponent as we wrote above. And we know that the logarithm is the inverse of the exponential function. Okay? We have a couple log laws here, just as a refresher. If you have log base a of any two numbers that are multiplying together, or any two expressions multiplying together, you can break this up into two logs that are adding, that have that same base you had in the original expression. If you have two expressions x and y that are dividing, you can break that up into two logs that are subtracting. And if you have an exponent on the stuff inside the log, you're allowed to bring that down. So for example, if I had log base 4 of, let's say, x times, I don't know, x minus 1, this would be log base 4 of x plus log base 4 of x minus 1. If I had log base 5 of x over x minus 1, I could rewrite this as log base 5 of x minus log base 5 of x minus 1. And if I had log base 2 of x minus 1 cubed, this would be 3 times log base 2 of x minus 1. There might not be x's in there, there could be actual numbers. still apply, and these apply to ln as well. Okay. Now you also have change of base rule, which most of you probably only used if you really needed to be able to plug things into your calculator. But your change of base said that you have the log with any base a and inside stuff b. You can rewrite this as log b over log a. Remember, these would have a base of 10 since there's no base specified there. Remember, if there's no base specified, it's 10. And then this means that you could change it to any other base that you want. You could rewrite it as log base c of b, log base c of a, or we could do a log with a base of e, which would be ln. Okay, so that would be new there. So if we want to solve, just a reminder, if you're solving a logarithmic, if you have logs on both sides, or in our case, lns on both sides, if you have a single log or a single ln, then the inside stuff must be equal to each other. Otherwise, we usually rewrite it in exponential form. So this first one, we have ln of x equals 3. So we would want to rewrite this in exponential form. If you'd like to, you can rewrite as log base e of x equals 3. But if you can help it, we don't want to get into that habit of always having to do this. You will need to be comfortable with ln if you plan on taking more math courses. So I wouldn't get into the habit of always changing it to log base e. It's going to be more work in the long run. But for now, if that helps you, you can. So we've got log base e of x, or ln of x, equals 3. If I rewrite this in exponential, I'm just going to write my rule on the top here just so that we can move a little quicker without having to scroll back and forth. So my base here is e, my exponent would be 3, and my b value is x. So I'd have e to the 3 equals x, and we'll leave it like that. We're not going to plug that into a calculator. The next one, we would have a base of e. So we have e to the 3 equals x plus 2. Because my b value here is this whole x plus 2, my c is 3, and my base is e. Then I would need to subtract the 2 from both sides, and I would get e to the 3 minus 2 equals x. Again, we're going to leave it there. If we want to find the inverse, again, a reminder from last lesson, we swap x and y, resolve for y. So I'm going to have x equals 2 to the y minus 1. We want to find y. So to start, I'm going to move the 1 over. Now, as soon as I have an unknown exponent, I will want to log both sides. And when you log both sides, you want to pick the base of the exponential that you're trying to solve here. So I want a base of e, so I'm going to ln both sides. So if I ln the left, I get ln of x plus 1. If I ln the right, I get ln of e to the 2y. I'm going to use my log laws to bring that exponent down in front. Many of you will do that in one step. You won't use 2 separate steps for this. Now, once I do this, I know ln e is equal to 1. So I can stop writing ln e. So I have ln of x plus 1 equals 2y. Divide by 2, and I get ln of x plus 1 over 2 equals y. You can stop here if you want, but there are other ways we can simplify. We can rewrite this as half ln x plus 1. That's fine. Okay. We could bring this 1/2 back into the ln as an exponent. And we know if we have an exponent of 1/2, this is the same as a root. So we have many different representations. These are all fine. So really all today is a refresher of log laws and how to evaluate a logarithm. introducing ln as a new logarithm that you need to be comfortable dealing with. So ln, all of our log laws apply. All ln is a log base e, but it's a shorter way of writing that. Natural logarithm. Again, you can change these all to log base e if you want, but I would not get into that habit if you help it. You will need to be comfortable with logarithms long term.